As a parent or mentor, you have the awesome opportunity to help a young person build a future. So if the future they want is in the military, take the time to learn more at todaysmilitary.com, because their success tomorrow begins with your support today.
Prepararse para lo próximo que viene es una parte importante en el proceso de hacerse un adulto. De modo que si su hijo le dice que quiere unirse a las Fuerzas Armadas, se está preparando para un reto. Visite todaysmilitary.com, porque su éxito del mañana empieza con su apoyo hoy.
This is SpaceTime, Series 23, Episode 47, for broadcast on the 18th of May, 2020. Coming up on SpaceTime, one of the oldest objects in the Milky Way galaxy, growing doubts about one of the universe's fundamental constants, and Australia and the United States threatened by an out-of-control Chinese rocket. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Astronomers have discovered an ancient globular cluster that appears to be a staggering 13.6 billion years old. Not bad, considering the universe itself is only 13.8 billion years old. By the way, that makes this one of the oldest known objects in the Milky Way galaxy. A report in the journal Research in Astronomy and Astrophysics claims the cluster, named NGC 6652.4-05957, was identified by its unusual spectroscopic signature. Globular clusters are ancient, densely packed spherical collections containing hundreds of thousands to millions of stars. The Milky Way galaxy has between 150 and 160 globular clusters orbiting in its galactic halo, while Andromeda has an estimated 500. The stars in globular clusters are very tightly bound by gravity, and spectroscopic observations suggest the stars were all originally created at the same time in the same molecular gas and dust cloud. The exact origins of globular clusters remains unclear, with some astronomers suggesting they're significantly different from dwarf elliptical galaxies not to have been a galactic core. Because of their distance, always hanging around on the outskirts of galaxies, globular clusters can be very difficult to examine. So the study's authors, Margarita Sharina from the Special Astrophysical Observatory and Vladislav Szymanski from the Kazan Federal University, came up with the idea of researching the spectra of full star clusters. So they developed a special software package called Cluster, and they've already used it to model the spectra and determine the fundamental characteristics of almost 40 globular clusters. But when they analysed the spectra of NGC 6652.4.05957 obtained from the Sierra Tololo Observatory, they found it had an unusually high metallicity compared to other globular clusters. Metallicity refers to any elements other than hydrogen and helium, the atoms produced in the Big Bang. The spectroscopic analysis also found some anomalies in the ratios of several elements, including carbon, nitrogen, sodium, magnesium, calcium, and titanium. The authors suggest this could be due to the cluster passing through the galactic disk of the Milky Way on numerous occasions, in the process amassing heavier elements during each pass. This is SpaceTime. Still to come, growing doubts about one of the universe's fundamental constants, and Australia and the United States threatened by an out-of-control Chinese rocket. All that and more still to come on SpaceTime. A new study suggests that one of the fundamental constants of the laws of physics doesn't appear to be quite so constant across the universe and seems to change depending on where you are. The findings, reported in the journal Science Advances, adds to a growing body of work showing that the strength of the electromagnetic force, one of the four fundamental forces of nature, seems to vary across space-time. The observations could have profound implications for science's understanding of the cosmos, because it supports the idea of directionality in the universe, in other words, an isotropic cosmos. According to the Standard Model of Particle Physics, the foundation stone upon which science's understanding of the universe is based, the fine structure constant, which is a measure of the strength of the electromagnetic force that keeps electrons attached to their atoms and without which all matter would fly apart, should be exactly the same everywhere in the cosmos. The fine structure constant is a constant because it's a dimensionless number, a ratio involving the speed of light, Planck's constant, and the electron charge. The problem is, the study's lead author, Professor John Webb from the University of New South Wales, keeps finding tantalising evidence to the contrary. Webb and colleagues have now been measuring this apparent change in the fine structure constant for more than 2 decades. 10 years ago, the authors were observing light from some 300 distant quasars as it passed through gas in galaxies up to 12 billion light-years away, providing them with insights into the universe when it was just a fraction of its current age. Quasars are among the brightest objects in the cosmos. They're powerful beams of energy generated by matter being ripped apart as it falls into a supermassive black hole. As this quasar light passes through the galaxies, specific wavelengths are absorbed by the gas, resulting in an absorption spectrum, telling scientists about the chemical composition of that gas. But unexpectedly, Webb and colleagues noticed that the fine structure constant appeared to be different depending on which direction they were looking. Webb says it appeared to be getting stronger in one direction and weaker in the other. Webb's initial observations used the giant 10-metre Keck telescopes in Hawaii. In order to eliminate any equipment aberrations with the telescope, the authors collected data from a second observatory, the Very Large Telescope, or VLT, in Chile's high Atacama Desert. The VLT looked at a different part of the sky, but it came up with findings consistent with Keck, showing the same rate of change and in the same direction. As astronomers look at more and more distant objects in space, they're also looking back further in time. So Webb and colleagues looked at even more distant quasars, some 13 billion light-years away. In a never-before undertaken observation, the authors carried out 4 measurements of the fine structure constant along the one line of sight to a quasar. Now, individually, these 4 measurements didn't provide any conclusive answer as to whether or not there really was any perceptible changes in the electromagnetic force. However, when combined with other observations undertaken by other scientists unrelated to Webb's work, the differences in the fine structure constant became evident. They found hints that the fine structure constant really was different in certain regions of the universe. The observations add to evidence that electromagnetism seems to be gradually increasing in strength when looking back in one direction over distances of 12 billion light-years, while looking back over the same distance but in the opposite direction shows an apparent decrease in strength. And yet in all other directions, the fine structure constant remains just that, constant. Now you may recall that last month on SpaceTime, we reported on the work of Konstantinos Migos from the University of Bonn, whose observations, reported in the journal Astronomy and Astrophysics, suggested that the universe is expanding at different rates in different directions. Astronomers generally agree that the universe started with a Big Bang about 13.82 billion years ago, and it's been continuously expanding ever since. That rate of expansion appears to be accelerating due to a mysterious force called dark energy, but that change in the rate of expansion still appears to be the same in all directions. Migos' research examined the relationship between the temperature of hot gases pervading a galaxy cluster and the amount of X-rays it produces, known as the cluster's X-ray luminosity. The higher the temperature of the gas in the cluster, the higher the X-ray luminosity is. And so once the temperature of the cluster gas can be measured, the X-ray luminosity can be estimated. And here's where it gets interesting. Clusters of the same temperature and located at similar distance should appear similarly bright. But that's not what they observed. Instead, Migos and colleagues saw clusters with the same properties and with similar temperatures, which appear to be less bright than what we would expect in one direction of the sky, and brighter than expected in another direction. And the difference was quite significant, around 30%. Even more interesting, these differences weren't random, but they had a very clear pattern depending on the direction of the sky you're observing. Webb says if the fine structure constant really does vary not just with time but also space, that would require a major rethink of quantum mechanics and our standard model of particle physics. He says if the fine structure constant is different in different parts of the universe, then that could mean different properties for chemicals and even biology. According to Webb, a 4% change in the fine structure constant would mean differences in the production of elements, which would affect how stars burn, and change the production of heavy elements such as those needed for the formation of life.
What's new about the work is that we've pushed it to much higher redshift, or if you want to think in terms of distance, much greater distance away from Earth, or much closer to the Big Bang in time. So we've pushed this right back into the early universe, further than there's ever been pushed before. We've gone into the infrared part of the spectrum for the first time, which has allowed us to do this. Before, we had lots of observations, but our observations were all bunched up below a redshift of 3. We've got measurements from 5.5 out to 7. What that means in terms of look-back time, so the universe is about 13.8 billion years old according to the standard model. We've gone within about 800 million years, within about 0.8 billion years of the Big Bang. So we've gone back very early now with these observations. Then we've combined these new observations. There is only one quasar in that Science Advances paper. It gives 4 measurements along the line of sight. And those 4 measurements we've combined with a bunch of other measurements which we've previously made closer to us in time, if you like, and then look to see what happened to the directional signal that was already hinted at by the data. And the answer is it doesn't go away. You know, the new data points are consistent. By themselves, they don't prove anything. It's still tentative. Unfortunately, it's still tantalizing, but we get the same directionality. And these new measurements certainly do not conflict with the suggestion that there could be a directionality to the universe. In fact, a directionality signal is preferred over non-directionality when you take the data set as a whole. So that's what's new. We've got measurements which go much earlier, far more distant from Earth, closer to the Big Bang in time, and they still continue to support the idea or this notion that there could be a directionality in the laws of physics. That's what's new.
So what this is telling us is that if you look in one direction, the value of the fine structure constant is different to what it is in another direction, and yet if you look in other directions, it matches what the existing figures for the fine structure constant are.
That's right. And the interesting thing is, the other new aspect to this, since we last spoke, which is a long time ago.
About a decade, actually.
Yeah, I know. Time flies, yeah. The other interesting thing is that there have been a bunch of other measurements. Now, this MICAS measurement is one of a bunch. There are measurements involving the cosmic microwave background, the bulk velocity flow of large numbers of galaxies, supernovae measurements in the MICAS observation X-ray emission from galaxy clusters, and so forth. There's a bunch of other types of observations which are completely independent of the sort of work that I'm doing on the fine structure constant and don't directly involve the laws of physics, but involve distribution of matter. And these things also suggest a directionality. Perhaps individually, each one, none of them especially compelling, although statistically significant at some level, but they all seem to line up on the sky within the errors. The errors are still big, but it's a very interesting situation. Now, there's a chance that it's a huge cosmic conspiracy or a cosmic fluke, in which case, that's just one of those things. But on the other hand, it's something that really does need exploring. There is this apparent coincidence between a bunch of different measurements. And the fine structure one, which we originally published back in 2011, we suggested that there was that sort of signal in the data. Since then, all these other data points have been added to it. So it's a really interesting situation.
The fact that these things are happening using different methods of observation, that's significant, because if you're getting the same results using the same method, then that's one thing. But if you're getting the same sort of results, the same observations, by using different methods, that's actually very significant. That starts to become something that needs urgent investigation, surely.
Well, I would say so, yeah. There was a paper a while back by some Greek authors who put all these measurements together and assessed as a whole the statistical significance. And it was looking pretty, I wouldn't say compelling, but it was certainly statistically significant.
Are we up to the 3 sigma level yet or something like that?
Well, we're above 3 sigma with just our measurements alone.
Wow.
And individually, most of these are above that. But, the kind of like the gold standard, if you like, is often taken as 5 sigma.
Yes.
Whether we're up to 5 sigma with this collection of measurements or not, to be honest, I don't know. I haven't looked into that. I'm focused completely on the work that I'm doing, which is trying to get the best possible measurements I can of the fine structure constant. And we're at it's actually in our paper, maybe about 4 sigma or something like that.
For our listeners, 5 sigma was enough to give us the Higgs boson as being there, as existing, as being real. So
That's right.
You're obviously very close. It's an important point in this research.
Yeah, you're right. 5 sigma is what got people convinced about the Higgs boson. We're getting there. Luckily, there's some fantastic new instrumentation coming along and new facilities, which mean And this means that we really can improve the data. It just takes time and a lot of effort. There's a new instrument on the European Southern Observatory VLT called Espresso, which has a new means of calibrating data. The old data was precise. The new data is far more precise. Data is coming along. We're getting better measurements. A couple of months back, we actually had time to make new measurements on all 4 VLTs at once. This was unprecedented, I think. All 4 8-meter telescopes were hooked up by optical fiber, and each optical fiber was then brought together and fed into one instrument to observe one quasar to get a very high signal-to-noise, good signal on that one quasar. We've got that data. The observations were successful. We're working on that at the moment. We don't have an answer yet, but that's coming. Just one of the new things that's coming. The measurement that we're talking about at the moment came from another instrument on the VLT called X-Shooter, which is an infrared instrument. Infrared observations of this sort have been catching up with the optical ones. It's harder to build these high precision, high sensitivity instruments in the infrared, but the technology has got better and better. That's what this new paper is about, the first infrared measurement, enabling us to go right back to within 800 million years of the Big Bang.
Explain the fine structure constant to us.
The fine structure constant is a dimensionless ratio of 3 quantities. It involves Planck's constant, the speed of light, and the charge on the electron. And it's a dimensionless ratio involving those 3 quantities. The fact that it's dimensionless, has no units, is very important because it means it's more fundamental than a quantity like, for example, the speed of light, which does have dimensions. So this is the sort of quantity that people like me focus on because you don't need the units to make the measurement. The fine structure constant itself is the number that physicists use to parameterize, to provide a measure of the strength of the electromagnetic force. There are 4 forces that we know about, electromagnetism and gravity, and then the 2 forces that act inside atoms, the strong and the weak force. And so it turns out that the electromagnetic force, as measured by the fine structure constant, is the one that we can perhaps most easily make measurements of.
And it's a constant, which means it should be the same everywhere. And this research is showing that there's a growing possibility that it's not. That really has got to be affecting the foundation stones of our understanding of physics.
That's right. The physics that we've been using for a very long time is based on the assumption that the laws of physics are the same throughout the history of the universe. They're the same everywhere. If you take Einstein's theory of gravity, for example, it's based on what's now given the name the Einstein equivalence principle, which states that the laws of physics are the same everywhere, and they always have been. That assumption makes it easier for theoreticians to build equations which give us predictive power and which describe the observations that are made of the universe. Without those assumptions, everything gets very much harder. So it's very appealing to have these simplifications built into our standard models of physics. But simplification isn't necessarily part of the real universe. It may be, it may not be. And modern theories, string theories, do permit, they have that option built into them that the fundamental constants should vary. To put it maybe slightly differently, in these new theories of everything, there's nothing that stops the fundamental constants changing, nothing fundamental that stops them changing. And so many theoreticians actually expect that at some level we're going to see such changes and have constructed new theoretical models to describe how that happens.
The standard model does have its problems. It can't explain dark energy and it can't explain dark matter, at least not yet. That's got to be a hint that there has to be new physics beyond what we know.
I would have thought that everyone would agree with that statement. You're right. The standard model of cosmology works very well if and only if most of the energy content of the universe is not in the form of protons, neutrons, and electrons, the stuff that we're made of, but has to be in the form of dark energy and dark matter as well. Without those assumptions, you can't make the standard model work. So there is certainly something new that we don't know about. Either the standard model is wrong, or these things, dark energy, dark matter, do exist. So something at some point will give.
Dark energy couldn't just be an example of the Casimir effect on a cosmic scale, and dark matter isn't just a new type of neutrino that we haven't discovered yet. Or maybe it is. Maybe there is an axion, although the evidence doesn't seem to point to that.
Well, people keep on placing upper limits on different candidates for dark matter particles, and the trouble is that, even when you add up all of the upper limits, you can't quite get to the amount of dark matter that you need to explain the observations of galaxy rotation curves and various other things.
That
so we haven't identified.
Is hard to reach.
Yeah, the dark matter hasn't all been found yet. There's lots of candidates. I guess most people would regard the dark matter not as the worst mystery, if you like, that dark energy is, because we really don't know what it is. We really don't have a clue as to what dark energy is. But on the other hand, it is, in support of the Standard Model, it is fascinating that the Standard Model has so many incredible successes and works so very well in many different ways. We get amazing predictions from the models which predict the abundances of the light elements. To a significant extent, the universe does appear pretty isotropic. This is, of course, what we're discussing, whether it's completely isotropic. But, the CMB data is isotropic to within 1 part in 100,000. But is it completely? There is a residual signal in CMB data, which has not yet been, I think, explained completely. And there are all these other observations which seem to...
The Hubble constant doesn't work in the CMB, and when compared to other measurements of distant supernovae.
Yeah, well, the supernovae are interesting. There have been many papers which have looked to see whether there is a directionality in the supernovae data, which, of course, as you know, led to the Nobel Prize for the accelerating expansion of the universe. And as far as I know, the jury is still out, but there are several papers which suggest that, in fact, there is a directionality. And that's another direction which actually lines up with our fine structure constant dipole direction. There
seems to be all these little clues in different areas of physics which are all pointing in that direction.
There's certainly something interesting going on. As I say, whether it's a cosmic coincidence or not really remains to be seen. People are trying. We're just pushing ahead and trying to make better and better measurements. We've been working on this for a while. There is still plenty of data that we've got that we're analysing. We think that in about a year we'll be able to get to the first 1,000 measurements of the fine structure constant. We're about halfway there at the moment. That may bring forth some answers. It's a slow job because these measurements are very complicated, but we're bringing in new methods. We've got some new AI methods that can now analyse the data in completely objective ways and do so automatically on sufficiently powerful supercomputers.
That's Professor John Webb from the University of New South Wales. And this is SpaceTime. I'm Stuart Gary. Still to come, Australia and the United States threatened by an out-of-control Chinese rocket. And later in the Science Report, a new study warns that some kids with COVID-19 antibodies are starting to show signs of a new inflammatory syndrome. All that and more still to come on SpaceTime. Australia and the United States have escaped being hit by a deliberately out-of-control Chinese rocket. The Long March 5B rocket core stage was the most massive object to have made an uncontrolled atmospheric re-entry since the 39-ton Russian Salyut-7 spacecraft crashed in Argentina in 1991. The Long March 5B had earlier launched a prototype of China's new space capsule on a test flight from the Wenchang Satellite Launch Center on the island of Hainan in the South China Sea. The 54-metre-tall launcher is designed to inject payloads directly into low Earth orbit using only a core stage and strap-on boosters, and without the need for any upper stage. Now, of course, that's a lot cheaper than adding 1 or 2 additional stages onto the stack, but it means the core stage also has to end up in orbit, instead of dropping away, as would normally happen. And that's a problem for the Long March 5B because it's not equipped with reignitable engines, so it can't undertake a deorbit burn and controlled re-entry. And that means that mission managers can't choose when or where the rocket re-enters the atmosphere. Usually, spent satellites and disused rocket stages are brought down in a controlled manner that sees them re-enter on a predetermined course, allowing most of the spacecraft to burn up in the atmosphere, with any surviving segments crashing into an internationally designated impact zone in the South Pacific Ocean between New Zealand and Chile. However, because of the way Beijing designed the Long March 5B, that was always going to be a hit-or-miss affair, because factors including atmospheric drag and solar activity, which constantly change, would ultimately be the determining factor in deciding the rocket's rate of orbital decay. And the sheer stupidity of this uncontrolled re-entry approach became clear when it was realized that based on its atmospheric drag and orbital decay rate, while it was likely to be the Long March 5B's final orbit, an ellipse ranging from 139 out to 162 kilometers in altitude would result in the wreckage crashing to the ground along a track running across Australia, the United States, and Africa. Luckily, and it was just luck, the 30-metre-long course stage kept going long enough to miss Australia and the United States, being spotted as only a streak in the skies some 170 kilometres above New York City. The US Air Force 18th Space Control Squadron, which was tracking the spent rocket stage, reported that it apparently impacted in the North Atlantic Ocean about 160 kilometres off the coast of the West African nation of Mauritania. However, shortly afterwards, reports began emerging of damage to buildings and properties in two towns along the Long March 5B's ground track in the Ivory Coast. Images uploaded to social media have shown burnt wreckage, including metal fragments and segments of what appears to be cryogenic oxygen transfer pipes on the ground in the two towns. Of course, out-of-control re-entries are nothing new for China. As we reported at the time, just 2 years ago, China's 9-ton Tiangong-1 experimental space station also came tumbling back down to Earth after telemetry and control were lost and the spacecraft's orbit began to decay. And in an ironic case of history repeating itself, just as with today's COVID-19 coronavirus pandemic, China didn't bother telling the rest of the world about their broken-down space station until other countries had already detected their out-of-control spacecraft's disintegrating orbit. Of course, back then, China couldn't find an astronomy version of the World Health Organization to cover up for them. And so the European Space Agency issued a worldwide alert and began an international campaign to monitor the spacecraft's descent. It eventually re-entered Earth's atmosphere over the southern Pacific Ocean northwest of Tahiti on the 2nd of April 2018. Meanwhile, the primary payload for the Long March 5B's launch, a prototype of China's new manned space capsule, has returned safely to Earth following its 3-day orbital test flight. The capsule touched down in the Dofang landing zone in northern China's Inner Mongolia. The Long March 5B had placed the 21.6-ton 2-module capsule into an initial low Earth orbit. The capsule then used the main engine of its service module to raise its altitude to an 8,000-kilometre apogee highly elliptical orbit, proving it's got the delta V's for much longer distance spaceflight. It then undertook a high-speed atmospheric re-entry, testing its new detachable heat shield. The flight also tested the capsule's new avionics, the performance of its new orbital maneuvering system, a new parachute deployment system, and a cushioned airbag landing system. As part of the mission, China also tested a new flexible inflatable cargo return module, basically a low-density supersonic decelerator with its own inflatable heat shield. However, the decelerator failed during re-entry. The new reusable capsule will eventually replace China's current 3-person Russian Salyut-based Shenzhou spacecraft. It'll be used to carry up to 6 taikonauts, or alternatively 3 taikonauts and 500 kilograms of cargo, to Beijing's planned new 3-module Tiangong or Heavenly Palace space station. China's planning at least 12 missions to construct the new space station sometime around 2022. The Communist government's official Xinhua news agency also says the new spacecraft will eventually be used to carry taikonauts to the moon by the end of the decade. This is SpaceTime. Still to come, the Science Report, and disturbing news stories about kids with COVID-19 antibodies starting to show signs of a new deadly inflammatory multisystem syndrome. And paleontologists have discovered the earliest known hominid remains in Europe. All that and more still to come on SpaceTime. And time now to take a brief look at some of the other stories making news in science this week with a Science Report. A new study warns that some kids, teens and young adults could be at greater risk of severe complications from COVID-19 than previously thought, especially if they already have underlying health conditions. It all comes as a bit of a shock, because all the previous evidence has suggested that kids suffered only very minor symptoms from COVID-19, and most were completely asymptomatic. No one's exactly sure why, but it could be because kids' immune systems are more immature than those of adults and somehow react differently. However, over the past few weeks, there have been a number of disturbing reports that kids either with COVID-19 or with COVID-19 antibodies are becoming seriously ill, and some are even dying. That's prompted a new study in the Journal of the American Medical Association, which is describing a series of characteristics being suffered by seriously ill pediatric COVID-19 patients. The findings are based on a small group of just 48 kids and young adults up to the age of 21. It found more than 80% of those suffering from the new syndrome had chronic underlying conditions such as immune suppression, obesity, diabetes, seizures, or chronic lung disease. Of those, 40% were dependent on technological support due to either developmental delays or genetic anomalies. More than 20% experienced failure of 2 or more organ systems due to COVID-19, and nearly 40% required a breathing tube and ventilator. At the end of the follow-up period, nearly 33% of children were still hospitalized due to COVID-19, with 1 on life support and 3 still on ventilator support. At least 2 of the children admitted during the 3-week trial period have since died. This study was prompted by reports from pediatricians that a number of COVID-19 infected children are presenting to intensive care units with a range of unusual and varied symptoms. Doctors are provisionally referring to this new autoimmune disease as pediatric inflammatory multisystem syndrome temporarily associated with SARS-CoV-2, or PIMS-TS for short. The symptoms include prolonged fever, abdominal pain, low oxygen levels, rashes, conjunctivitis, irritability, and changes in the oral cavity, most noticeably a strawberry tongue. And closer clinical examinations also revealed that many of the kids suffering from this disease have developed inflammation within their hearts, characterized by inflammation of the coronary arteries. Now, these symptoms are all very reminiscent of what's observed in a rare childhood illness known as Kawasaki disease, which mainly affects kids under 5. Now, it's this overlap of all these symptoms which has prompted many specialists to speculate that COVID-19 is somehow triggering Kawasaki disease in these children. The Western Australian government has launched an investigation after State Premier Mark McGowan's office was targeted in a cyber attack by the Chinese military. The New York Times is reporting that an email sent to a member of the Premier's staff from a contact in the Indonesian embassy in Australia contained an attachment that included an invisible cyber attack tool known as AriaBody. AriaBody is used by a group of People's Liberation Army hackers known as NACON, allowing them to remotely take control of a computer, undertake searches, and copy, delete, or create files. The Chinese attack was detected and blocked by the Israeli cybersecurity company Checkpoint Software and is now being investigated by the Australian Cybersecurity Centre. China's communist government carried out similar cyber attacks last year, targeting Australian federal politicians and universities. This latest report follows last week's discovery that China, Russia and Iran have been carrying out cyber attacks targeting British research facilities working to find a vaccine for the COVID-19 coronavirus. And warnings this week that China's also been launching cyber attacks in the United States, also targeting research facilities working on COVID-19 vaccines. Paleontologists have discovered the earliest known Homo sapien remains in Europe. The findings reported in the journal Nature have dated the early modern human remains to some 45,000 years ago. The finds, excavated from Bakukiru Cave in Bulgaria in southeastern Europe, included a tooth and numerous bones. The digs also uncovered a number of artifacts, including ornaments such as pendants made from bear teeth. The finds show that modern humans had already moved to Europe while their Neanderthal cousins were still very common there. A new study has shown how expert scientific groundwater advice was systematically ignored or dismissed as part of the Adani Carmichael mine approval process in Queensland. The findings, reported in the journal Nature Sustainability, are based on a new and extensive scientific review of Australian authorities' responses to serious flaws and data gaps in Adani's analyses and predictive modelling. The paper highlights the systematic way that expert advice from independent scientists was simply dismissed or ignored in the approval process for the Carmichael coal mine by both the Queensland and federal governments. And that's the show for now. SpaceTime is broadcast on Science Zone Radio by the National Science Foundation in Washington, D.C., and through both iHeartRadio and on TuneIn Radio. Or you can subscribe and download SpaceTime as a free podcast through Apple, Stitcher, Bytes.com, Pocket Casts, SoundCloud, Spotify, YouTube, Audio Boom, Podbeam, Android, Castbox, from spacetimewithstuartgary.com, or from your favorite download podcast provider. You can help support the show and the work we do by visiting the SpaceTime online shop and grabbing yourself a few goodies, or by becoming a SpaceTime patron, which gives you access to commercial-free double-episode versions of the show, as well as bonus audio content and other rewards. Just go to our Patreon page through spacetimewithstuartgary.com for all the details. If you want more space time, check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as loads of images, news stories, videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word and in lowercase, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, at SpaceTime with Stuart Gary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to www.facebook.com/spacetime with Stuart Gary. SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.
Hello, saver. Whether you're saving for that trip to the tropics or saving for an emergency, now is the time to take advantage of Wells Fargo's savings options. Wells Fargo offers savings accounts that can help you save towards your goals. So, what are you saving for? Visit a Wells Fargo branch or wellsfargo.com/save to open a savings account today.
Wells Fargo Bank, N.A., member FDIC.